Okay, we're going to do a lot in this video. I'm going to show you side of the screen, and on the right side I'm going to show you how to calculate the end reactions as we go through this. So the first thing that we want to do on this is to draw a free body diagram, and in your notebooks, as you're doing those along, we're going to draw a line straight down, along here, and along here. And we're going to make room, have enough room here for 3 diagrams. So the first one we're going to make right along there. This is where a free body diagram is going to go. The other one's going to go right here, and that's where our shear diagram goes. And the last one we're doing is going to be our moment diagram down here. So I like to label these like so that I don't forget what I'm doing as I go along. So the first one is our free body diagram. I'm going to do this one in green. We have some end reactions here. Because this is a pinned joint, it can actually resist forces coming from the y direction and the x direction. So I'm going to draw a arrow here to end up as a reaction. And I like to call this the reaction at point A in the y direction. And then we have another reaction going to the right here. I like to put a little slash through my arrow. And this is the reaction at point A in the x direction. Point B over here is a roller joint, and so that can only resist in one direction. So I'm going to come up here and put my reaction here. And this is going to be a reaction at point B in the y direction. And the last thing we have is the point load at 8 feet coming down, and this is going to be 500 pounds. So the next step is to find the sum of the forces in the x direction. So I'm going to do the sideways E guy and do the forces in the x direction. And all those have to be 0. All the forces in the x direction have to be 0, otherwise this thing's moving around. You definitely don't want that in a building. So what forces are in the x direction? If I look over here, I have RAX is the only force acting in the x direction, left to right. So RAX goes right here, and since it's the only force, there it still is added up to equal 0. Right? So the next step is to do the sum of the forces in the y direction, and those have to be 0. So first step here is to go through, and we're going to find what are the forces in the y direction. So up and down I have 500 pounds. Since that's going in the downward direction, it's going to be negative. And I have RBY, which is positive since it's going up. And I have RAY, and that's positive since it's going upwards. Alright, so we're going to, and once again this is all equal to 0. We're going to try and do some rearranging here. I'm going to add 500 pounds to both sides so that I get my formula, or my variables, all by themselves. So that ends up being 500 pounds equals RBY plus RAY. And we really can't do anything more with this formula until we know either RBY or RAY. So we're going to set this formula aside and we'll come back to it. And so the last thing to do is the sum of the moments. The sum of the moments in the sum of the moments about point A. So we're going to act as if this thing is pinned right here at point A, and these forces here and here are going to cause that rotation around that point. So the sum of the moments about point A, those all have to add up to be 0. So we have some forces that are going to cause that rotation. We have that 500 pounds here. We have the reaction RBY, the reaction at point B in the y direction, are both going to cause a rotation. And a moment is a force at a distance. So there's my force. And then we're going to figure out how far is it away from point A, since we said this was in respect to or about point A. So I'm looking here. This is 8 feet away from point A. and that's 500 pounds. So I'm going to multiply 500 times 8, and since this is causing a clockwise rotation, so if I push down here, that's going to cause this to move around this way, which makes that a clockwise rotation. Let me clean that up a little bit. So that's going to be negative. I'm actually just going to write this here so I don't forget that counterclockwise is positive and clockwise is negative. And the other force that's happening here is RBY. And RBY is 16 feet away from point A. And so I'm going to set all this to be equal to 0 again. These are all my forces here. And all that is equal to 0. So 500 times 8 is 500 times 8 is 4,000. So that's going to be 0 equals negative 4,000 plus sub RBY times 16. Alright, so I'm going to add 4,000 to both sides here to get my RBY by itself. Times 16. And then to get RBY by itself, we divide by 16 to both sides. And 4,000 divided by 16 is 250. And once again, that's in pounds. So RBY is equal to 250. And I like to box out my answers. And so now that we know what RBY is, we can come back up here to our sum of the forces in the y direction. So I've got 500 pounds here equals RBY is 250 and plus RAY. And you subtract 250 from both sides, and I end up with 250 pounds for RAY. And once again, I'm going to box this here. So now I know my end reactions. The next step is to go over and we're going to work on our shear diagram. And we're going to use these two numbers to start our shear diagram. So I'm going to switch colors again. We'll use orange for our shear diagram. So this is right here, 0 shear. That line represents 0 shear. And my end reaction at point A is 250. So I'm actually going to go up 250 pounds. And my end reaction at point B is 250. So I'm going to go down 250 pounds. And you try to make these symmetrical so that I've gone up and down in the opposite directions in equal or proportional way. So now I'm going to come along that 250 until I get to that point load. And that point load lines up right here. So if I bring this line down, you see my point load lines all this up. So when I get that point load is 500 pounds. So I'm going to drop 500 pounds. Here's 250. And another 250. And then continue over. There's no other forces acting downwards along this line, so this isn't going to move. So there's my shear diagram. The next thing to do is to calculate what the moment is. And a moment is actually represented by the area underneath this line. So if we can find the area underneath that line of that box, that'll actually give us our moment. So remember, we went up 250 pounds, and so we went up 250, and if we go to the right along here, this is 8 feet. And you know that moments are measured in foot-pounds. So it makes sense that if this is 8 feet, and this is a rectangle, and this up here to the, on the left side is 250, so this moment is going to be 250 times 8, which is 2,000. So the area underneath here is 2,000 foot-pounds. So I'm going to come along here. We've got our line still coming down from that point load. And the area point where we have 0 shear, right there, is where the maximum moment is going to be. And so our maximum moment is going to be at 2,000. I'm just picking a point up here and calling that 2,000 foot-pounds. Right? So my line is going to be starting here at this point and ending over here. And since the slope of my line in this graph above is flat, it's going to be a nice straight diagonal line that goes up to 2,000 foot-pounds, and then another nice straight diagonal line which goes down to 0 on the other side. So this is our moment, and this is the maximum moment that I'm going to need to know later on. So there's really three numbers that we get out of this, or four really. I've got my force in the x direction at point A, my reaction at point A in the x direction. I've got this reaction at point A in the y direction. I've got this reaction at point B in the y direction. And finally, this number that I'm really needing, again, is the reaction, or this, moment over here. So this is the maximum moment that this beam is going to have to hold up, which is 2,000 foot-pounds. And that is everything that you need to know about doing beam analysis.